Okay, I think it started. Yeah. So, good afternoon, everybody. Dr. Jyoti, thank you for this opportunity. So, in this session, I will be giving an overview about the focus in one of the sub-verticals in the speech processing area uh, for health informatics. Essentially, earlier we used to call this as pathological speech processing, but speech processing for health no is a much broader umbrella under which pathological speech processing can be treated as one vertical. Especially of like any other field, with machine learning and deep learning making inroads into this sub-vertical of the speech processing area, that is for analysis of health information from the speech signal and using that for predicting or identifying some malfunctions associated with the human. Um, that has become more attractive and more prevalent because of easy way of collecting speech data in a remote manner. Of course, as usual, now these are some of the good references for the speech processing area. Essentially, nothing to do with the health part. Generally, if you want to get a first feel about the speech processing field, these are the books which are available. And these are some of the good books for machine learning and deep learning, which is a standard material. Of course, coming to the articles on pathological speech processing, there are many um, books. So, what I'm many articles. In that specifically, I am considering this article by Nicholas, Alice, and Schuller, which they have written on speech analysis for health, current state of the art and increasing impact of deep learning. So that is what is come. Of course, that is the main article which I am basing this talk. I have organized the presentation in the following way. I'll briefly introduce the significance of speech processing for health. Then I'll highlight the significance part. Then I will go for explaining in a domain agnostic way, and also most possible easiest way of introducing the field of machine learning and deep learning. So once we have that, there is, of course, when we say machine learning and deep learning, essentially we get to our mind unless specified. We are using all these approaches or tools from machine learning and deep learning for doing some tasks like regression, clustering, classification, compression, those things. Whereas there is something else which is prevalent once this deep learning became very powerful. What we call it as representation learning, or we most commonly we can also call it as feature representation learning. So in the deep learning parlance, representation learning refers to the features which are learned by the deep learning models. Earlier we used to do by standard signal processing techniques for getting reduced dimensional feature vectors. But there most of the time it was linear processing. In place of that, any deep learning model will do nonlinear processing. So accordingly, this is hypothesized to be a better feature representation compared to earlier methods. What, of course, that is being demonstrated in many tasks by the in practical applications. Then I will come to some of the results in the speech processing area for using deep learning. Then I'll briefly mention about some of the healthcare tasks using speech, touch upon them, and then I'll summarize my talk. Coming to the introduction part, the first question comes is, Generally, when we say diagnosis, we think about the traditional test reports or X-ray images or some other images, and use them, or some blood test report, all those things, and use them for health diagnosis. Whereas there are many health-related issues which can be diagnosed by using speech signal as the biosignal or physiological signal. That is one part. Of course, generally people, when we say speech-based diagnosis, we are, unless specified, we are focusing on pathological speech, but beyond pathology also, we can use the speech signal as a representative signal for health analysis. The factors that are favoring use of speech mode for diagnosis, first thing is it is non-invasive. So you don't have to adopt any invasive technique to collect the speech data. So further, most of the consumer electronic devices like smartphone, wearables, smartwatches, earpods, etc., they all come with microphones which are well optimized to the best possible SNR to collect the speech data. So in that way, the end customer need not invest to buy for separate sensor to collect some physiological signal. So with the existing consumer devices, we can collect the speech without any invasive manner. So that is one big plus for using speech mode for diagnosis. Second thing is, we can do a passive monitoring when we use speech. Passive monitoring, I mean, for example, if you go for ECG analysis or anything, always some sensors are stuck onto different parts of the body. It creates some, even EEG, anything, it creates some inconvenience for the person because they have to carry those sensors with them. Here, anyway, we are carrying these consumer electronic devices, and we also don't get intimidated by them because they are just staying in our pockets or in our wrist, and it will just monitor whenever we speak. The speech data gets collected and then sent it to the receiving point. So in that way, without any much effort and without any much disturbance to the subject, we can do a passive monitoring. The second thing is, third thing is, we can collect speech data from a diverse population. For example, if I take any other ECG data, any other physiological data like ECG, you collect the data from that person, and based on the experience of the doctor, the decisions are taken. That's perfectly fine. However, suppose there is a chance of subjective bias there based on the experience of that person. Alternatively, suppose if I train automatic models by machine learning or deep learning, by collecting speech data from a diverse population, at that point the subjective bias may be limited. So in that way, it may result in an unbiased or a more generalized diagnosis. These are some of the important factors which favors using speech-based diagnosis or making speech signal as a candidature for health analysis. Just to give a visual representation, you don't need to be in the field of speech. Just if you take, these are visible representations of the speech signal information. We call them a spectrogram. Of course, a variant of that spectrogram, which is now by further smoothing, which we call MEL scale filter bank. This is simple short-term Fourier transform based spectrogram, which is a time frequency representation. That further you smooth it through a standard MEL scale filter bank. The well-known perceptually motivated non-uniform filter bank. Just to emphasize only the wanted speech-specific regions, this is the right side blue plot we have. So this A and B refers to a normal speaker's speech, whereas C and D refers to an individual which is affected due to some health condition. In this case, it is a depression. When a person is under depression, so how, if I look into the speech signal, of course, at the first level, unless you pay attention, both look same, but you slightly pay closer attention, you can see the high intensity parts which are there are at different locations between the depressed individual speech and the normal individual speech. So what it says is, so this is what is, we use it as a representation for automatic processing. Now you can see this representation for a normal individual and this representation for the an individual having health issue like depression for the same text. When you see that, there is a significant difference in the time frequency representation. That shows that the biomarkers or the signatures associated with that particular health condition are embedded into the speech signal if you want to derive them or make use of them. So this is one case I have told, but any speech signal you consider, if there is a health issue with that individual, some sort of biomark will be available in the speech signal. Of course, the question comes, how do you say that? This is because, suppose if I am talking to my friend over phone, and when you engage that person in conversation, you can quickly make out if he is suffering from some health. Suppose if he is suffering from cold and flu, or he is tired, so you can make out the way he or she produces speech, or if he is depressed, or if this person is showing a suicidal thought, or if that person is swallowing something, all these things, any deviation in the production system due to cognitive process or the physiological process, that information gets manifested as a biomarker in the speech signal. So that shows that it is indeed possible to use the speech signal for health diagnosis. Then the next question is, I already mentioned in the previous slide, that why machine learning and deep learning for diagnosis? Mainly because you can learn from the digital data that you have, especially this machine learning and deep learning. You can use them by modeling, by building the models on the given data. And these models can be used for the assessment of the speech disorders. So that assessment will maybe for screening the at-risk individuals before they access the healthcare system. For example, that is what is one of the focus of the artificial intelligence field. Suppose I have variables with me, and in a non-invasive manner, the wearable device collects speech data whenever I am speaking to somebody or conversing somebody, and the machine learning and deep learning based system will constantly process that data and try to see whether this person showing any tendency with reference to health issue. So accordingly, it can alert his family doctor or her family doctor. Okay, so to pay attention to the person or something. Second thing is, even for a clinician, we do several instruments and chemical and biological based processing to get the test report and use that for furthering the treatment. Whereas without any of these tests, with the help of data, you can build models, and the test sample you compare with the models and then get some assessment report which can complement the tests that are being done by the clinician. It will add value to the tests that are already been done. It will make them to make a more what we call decisive assessment about any particular thing. Also, suppose especially for a mental health case, This patient comes at some time, takes an appointment, and have a session with the doctor and counselor or something, and go back. Now they will say, no, you practice this particular drill material or exercises and keep yourself monitoring. Let us meet next week for a discussion, next session. But from the time this session to the next session, unless the mental health person calls back and reports to the counselor or the doctor, there is no way we can keep tab on what is going on, how that person is progressing. And also generally it has been a feeling that unless the counselor or doctor makes efforts to reach out to that person by herself will not take initiation to call back to the counselor or the doctor unless it goes beyond. Whereas if I have this health-based, speech-based system, I can monitor them in a non-invasive manner. So in between the consultations, what do we have? So these are some of the favoring factors where we can do speech-based diagnosis, and especially using machine learning and deep learning, we can develop models which can complement the existing solutions that are there. They are not replacements, but they complement the existing solutions. If you see, when it comes to the health aspect of humans, which is the focus in this session, we collect various or monitor and collect various physiological signals, images and videos. So one such physiological signal is speech, and this speech carries several health indicators for depending on what task we are interested. Multi-dimension health indicators will be present in the speech signal. That is the, just like any other physiological signal, images or videos, speech also carries several health indicators. That is the first point where we want to use speech for health diagnosis. Coming to the field of computing, we have faster processor, more memory. We have automation. Of course, second level of automation with the artificial intelligence, and all systems are networked, and we have internet and cloud infrastructure available, and the latest trend of artificial intelligence is available. With all these things are the developments in the field of computing, which can be exploited for making health informatics affordable to everybody. Coming to the humans, suppose if you consider a human expert, either she is a clinician or she is a doctor, she exploits her cognitive ability and also through the sensory mechanisms tries to observe the different physiological signals, images and videos, and try to look for some unique features in the physiological signals, images or videos, or the unique patterns that are apparent in these signals. Based on her experience, which we call it as natural intelligence. With the help of that, she will be able to make judgment about what may be the reason or cause for the particular illness or disease. Now, so these are the three factors we are considering. One is the health aspect, which is available, that health information is available in the form of biomarkers in different physiological signals, images and videos. Speech is another one physiological signal where several health indicators are embedded into it. Computing, there is a lot of development in the field of computing in terms of processor, memory and artificial intelligence. Coming to the human experts, whether clinicians or doctors, they make use of their cognitive ability and sensory mechanisms and do what we call representation learning and pattern way of processing. And based on their rich experience, which we call it as natural intelligence, they will be able to make judgment. So these are the three dimensions which we are looking forward in this session, how they interplay with each other to come up with a framework for speech-based health informatics. Of course, we are witness to what is happening in the current scenario. Because of the advancements in the computing, it is revolutionizing the health field. So where which we used to have very good, very bulky hardware-based electronic systems for testing purpose, now are being replaced by simple or very slim software firmware systems with better identification rate or better identification of health issues because of the advancements in the computing. And of course, these advances in the computing will give us a chance to mimic some of the human abilities, which accordingly has its own new challenges and opportunities. There are several new fields that have evolved due to this thought process of mimicking the computing field, like human-computer interaction, pattern recognition, machine learning, deep learning, artificial intelligence. One notable contribution in the field of machine learning and deep learning is what we call representation learning and pattern way of processing. Representation learning is for feature extraction, pattern way of processing is building models or clusters. That's what. So, in this session, I will be explaining how we can indeed exploit this representation learning and pattern way of processing features of the machine learning and deep learning models for health diagnosis. So now I mentioned in the previous slide that speech signal carries several health parameters or health indicators. Let us see how it will be there. Because generally we are essentially focusing in speech technology development mostly in terms of extracting features which can model the vocal tract system information or excitation source. And most of the time our focus is on that. And we feel that no, the amount of information or biomarkers that are available in the speech signal may not be very prominent. However, if you slightly look into the production, perception process and comprehension process of speech signal, it's a very complex physiological and cognitive process. So we need to appreciate this point. When I consider the speech production, perception and comprehension, it's a very complex physiological and cognitive process. Okay. So accordingly, any slight change in the speaker's physical and mental state, it will affect the ability to control the vocal apparatus or the organs that we use for producing speech. If there is a slight change in the speaker's physical and mental state, affects the ability to control the vocal apparatus, which used to happen in a very healthy individual. So accordingly, that change in the control over the vocal tract apparatus can in turn alter the acoustic properties of the resulting speech. So this is very important. So speech production, perception and comprehension is a very complex physiological and cognitive process. Then suppose if there is a change in the speaker's physical or mental status, it will affect the whole speech production system or the apparatus. So when they affect or dynamically they change their behavior, the nature of the speech signal that is generated from them also will change. That is what is meant by it will alter the acoustic properties. Okay. So as this will affect the acoustic properties, that is the signal nature, naturally that biomarker information is being embedded into the speech signal. So then since speech can be easily collected, transmitted and stored, these voice-based applications for the remote monitoring of speaker states and the triads, including health, have become more visible nowadays. Essentially, if you see, now we're in the era of IoTs, Smart monitoring can be done at a low cost, smart monitoring technologies. Then we have deep learning models which can learn complex information from the raw data. And currently, because of digitization of the health field, earlier it used to be the data was a serious issue. Now also there is a limitation in the health sector because you don't have many subjects or individuals who can process the same ill health condition. So accordingly, compared to the other fields, the data may not be big. However, relatively compared to the earlier generation, definitely it will be a big data. Because of all these things, smart monitoring technologies, deep learning, and big data, they can help in early and remote diagnosis of various health conditions. Okay, so all the wearable devices will have smart monitoring technologies, and they sense the data and send it to the cloud. And in the cloud, the deep learning model can run on the incoming data and find out is there everything normal or there is some deviation predicted. So based on that, it can take that will help us early and remote diagnosis. Once does that, so accordingly that information can be passed on to the concerned doctor to take care of precautions such that the serious issue cannot happen at a later point of time. So that is how we can use the speech signal as an health. Of course, when you consider human interaction with the external world, we have 5 senses: this auditory mechanism, visual mechanism, smelling, tasting, and touching. As human experts, health experts, we make use of one or more of these senses to predict what may be the health issue which is prevalent in the given subject. Okay. Of course, sensory mechanism, through that we know it's a human-human interaction happens where the doctor will also be a human, and based on her experience and conversing with you, then she can make out some information from your auditory signal, also looking at your face, visual feature, and also smelling, touching, and all those things. We can come to know about what may be the possible health issue. Of course, it essentially what it will do is, suppose if I'm looking at the face of the person and listening to the speech signal simultaneously, audio visual sense, the doctor day in and day out looking into some similar illness condition, person's audio and visual signal, that also they can know what we, as soon as they touch or get through the senses, what it will do is, through the sensory mechanisms, the representation is passed on to the brain via sensory pathways. Then the human brain will process the incoming representation as a pattern. That is pattern way of processing. Of course, this is all acts under the direction of the cognitive process or a cognitive processing. Now, if you consider the existing, why this ML and DL, when I go for diagnosis and treatment, it is mostly based on experience. More experienced is the doctor or the clinician, better will be the possibility of predicting what may be the health condition of the person. Then that was earlier era where you had minimum testing devices or testing labs. Doctors used to completely rely on their experience. So accordingly, most doctors are on ground in terms of developing a very good rapport with the health subjects, and also with that sensory mechanisms, many times they can predict the health condition much better compared to what we do in the current generation. The subjected to the test reports. Now, in the current generation, what is happening is most of the doctors will not do any interaction with you in terms of um, based experiential aspect. They don't use. What they do use, they completely rely on the test reports. Once the test report comes, they also don't tell candidly what is the health issue. They will now continue the treatment based on the test reports that have come, and the treatment is suggested by the doctor. So nowadays, without test report, there is no way doctor can prescribe what medicines this subject has to take. Whereas now the prediction of a particular illness by the doctor by looking into the test report, of course, in a very, very difficult case, this experience of the doctor may be insufficient. So he's a novice doctor, he has not seen enough examples in his professional service career to make such a judgment. Alternatively, if I go for automation using machine learning and deep learning, even though in my clinic or my hospital the amount of data is less, if I then under that condition we can use this automation using machine learning and deep learning using big data from data science perspective. So the advantage this machine learning and deep learning that provides is using the large amount of digital data, you can build models and then use these models for predicting some suggestions to the doctor. Okay, now the doctors will have subjective reports or test reports coming from the conventional labs. Along with that, this AML and DL models also will provide some additional information which may not be directly obvious in the raw data as well as the ML and DL models. So these are the significance of that. This I mentioned. Coming to the speech production and health, speech production is a complex cognitive and physiological process. Biomarkers means it will embed several biomarkers starting from cognitive to physiological. Why I am emphasizing on cognitive? Because you are under depression. The whole speech production system or perception system, which is a physiological system, is fully intact without any malfunction. But still, you will feel the nature of the speech signal to be different compared to the normal case. So which embeds that the person that biomarkers are embedded into the speech signal even from a cognitive variation. If you are under depression or if you are under what we call when you have taken alcohol, intoxication, we call more commonly intoxication. So many other things. So, but each of them will leave biomark into the speech signal which can be exploited. Of course, we modeled the speech generation process, which we call it as vocalization, as an independent source filter operation. And our emphasis is mainly on source filter operation. So, however, for the health case, there may be yet another dimension of information presence, which is at the what we call it the prosodic level, higher model level, that also will have information getting displayed for different health conditions. Coming to the cognitive disorder, suppose depression or sleepiness, or you have fatigue, or you have any other mental health related thing, then it can potentially disrupt message planning and pre-articulatory functions. Okay, so can potentially disrupt message planning and pre-articulatory. For example, I'll explain in the following slide. When I want to generate speech using the speech production system, there is a lot of groundwork happens in the cognitive system. Those that is called as message planning as well as pre-articulatory function, that is neuromuscular commands to be generated for the message to be produced. The whole activity gets disrupted because of the cognitive disorder. For example, even without any cognitive disorder, if I take for speech, so under that condition, the whole, for example, the way the person produce or generate the speech signal will be quite different compared to the normal case. So that is before even generating the speech, that information is embedded into the signal because already there is a cognitive disorder. Similarly, there is a neuromuscular issues. There are many cases like dysarthric speech we call, where the production, that's a neurological disorder which will lose control over the muscles and the speech production system. So naturally what happens is, at that point, the nature of the speech signal generated will be quite different compared to the normal case. Also, if I look into the speech signal, it will affect the quality of the phonation, that is the nature of the sound quality. Then the way resonant frequencies are distributed. Then the articulatory coordination among the different sounds. Like that, many more factors are there. These are just to give an example for that. Of course, coming to the field of speech processing, some of you might have seen these slides earlier. It essentially focuses on studying the speech signal and associated methods for processing them to extract and model information. Okay. That generic objective goes without saying, even for the case of health also. Our goal is to study the speech signals and associated methods to extract and model information from the speech signal. In our case, information means any biomarker available as health indicator. Of course, predominantly we use information means message, language, speaker, emotion, and health. I am focusing on the health aspect and how this health related information can be decoded from the speech signal. We can use speech, different tasks like speech recognition, language identification, and so on, health condition recognition. Our focus is on health condition recognition. So earlier, we had feature extraction by signal processing and modeling by pattern recognition, whereas nowadays, both feature extraction and modeling happens by deep learning. Okay, now let me consider different parts of human-human communication. It can be oral, further oral can be verbal communication or non-verbal communication. In case of verbal communication, we have spoken language backing the generation process. Whereas in non-oral, it refers to written language or sign language. Because that person cannot produce this speech in the oral cavity because of maybe due to several reasons. Whereas the non-verbal communication will be gestures, body language, etc. That itself will be sufficient in a coded manner if you want to get some sense of any particular process happening. Now, suppose if you see what is required for speech production, perception, and comprehension, we need a talker, we need a listener, and the C represents the acoustic pressure, acoustic wave in the air. Now you can see the three discretized portions in the speech signals are the cognitive system of the talker, the physiological system of the talker, external environment, then physiological system of the listener, and E is the cognitive system of the listener. Now here, suppose if there is a problem with the cognitive system, there is a degeneration there is no coherence in what I am speaking. Suppose I am feeling sleepy, now I am short of words to produce the speech. So those are all the cognitive activity. Similarly, suppose if there is a malfunctioning in the speech production system, that will lead to B-type lead to physiological related health indicators. Similarly, when I go for the deep portion, that is the ear, even if there is a malfunctioning in the ear, it will not be able to efficiently transmit the information from the ear to the brain. So that will also lead to some health indicators. Then finally, the cognitive system of the listener, that is E part, which will also, if it is not functioning properly, then naturally the effect will be there on the resulting speech set. Coming to the speech chain of our producing and comprehending the speech. So at the linguistic level, we think about what message to be generated. So this linguistic level is internal to the cognitive system. So naturally, when there is no speech production, this linguistic level is a cognitive process. So accordingly, any issue with respect to the cognitive process, it will affect the linguistic level. When it affects the linguistic level, physiological level will not question. It will blindly take whatever the linguistic level information available and then send it to the next level of the this one. So physiological level we have. Then we have, again, it goes into external environment to have maximum transfer of the information. We go by that acoustic wave. Then from the acoustic wave to the listener ear, we will have this physiological level, which is in the inner ear, and then the linguistic level. So the disorder can occur at any of these four parts. Of course, this acoustic level is external to the production perception system. We don't consider. You can have issues with any of these things, and accordingly, we can develop a machine learning and deep learning based solution. Suppose if I go for feature extraction for acoustic modeling, which we used to do now also, we try to model this vocal tract cavity, which contains the mouth cavity as well as the nostrils, and there are movable parts like tongue, teeth, and lips, as well as the velum. So as long as all of them are working in a coordinated manner, including the vocal folds, that is the glottis, as long as they are these are functioning properly, so at that point of time, the speech produced will be equivalent to or matching well with the normal condition. Alternatively, if some portion is not working, say, for example, this velum, all of you might have seen, which is called as the Adam's apple. Suppose it loses the stiffness and just sags inside the body. So then that velum part, when it happens, because of the neural degeneration, if it is not functioning properly, its function is to completely seal off the nasal cavity when we are generating oral sounds, and completely seal off the completely wide open whenever the nasal sounds are to be generated. And this is ensured by the proper functioning of the velum. Suppose due to any reason, if that is not available, then you will not be able to produce oral sounds. You will produce, but it is highly nasalized because the nasal cavity is also coupled with the oral cavity. So such things we can try to improve in terms of when this velum, this one, we can measure the cause for that. So suppose it is highly nasalized, then we will be able to say that no, the velum, sagging of the velum has happened. Now doctors should take a view on that and what needs to be done for that purpose. Same thing should occur to any of the other moving parts in the body. Suppose if there is a problem in the lip, then you will not be able to completely close that pair of lips. So which will result in the absence of when absence of the natural sounding speech, it will again know it will be highly nasalized and less intelligible. So like this, you can have now many activities associated. So now with the help of speech production knowledge, we can build a model like this, which is a vocal tract filter and the lip emission and the source model, that is excitation source and signal processing. These are the physical models that have been studied in the speech production area, and this model has been proposed. Now the same model concept can be used for analyzing the health conditions. For example, if that health condition is affecting the vocal tract information, I can, since I have estimated the vocal tract information using this model-based approach, we can find out how much it is deviating compared to the normal condition vocal tract information. Based on that, they can take a call on call on the health condition. Similarly, for the source condition also, if there is a problem in the excitation source mechanism also, you can identify that. That is about any malfunctioning in the production organs can be identified by extracting the parameters representing the vocal tract system and the excitation source. Coming to the speech perception process, that a human ear, if there is any malfunctioning, of course, the whole ear is divided into three parts: external ear, outer ear, middle ear, and inner ear. Inner ear is essentially what we call it as cochlea, and middle ear is what we call soft bones, ossils. So if there is a malfunctioning in any one of these areas, for example, if there is a breakage in the eardrum, you will not be able to transfer the information from the eardrum to the next level. Suppose if there is a malfunctioning in any of this chain of soft bones that are present, that will also reduce the efficacy of the person. Similarly, internally also in the cochlea, there are small inner hair cells, sensory mechanisms. If they fail to function, to that extent, the information transmitted to the higher level will be lower. So in that way, all these things will become apparent when we are recording the speech. Of course, the question comes, in the perception system, how do a speech signal will give a biomarker? Suppose if the efficiency or perceptual hearing sensitivity of that person ear has gone down due to malfunctioning of these parts, naturally the speech produced by that person will have a different nature compared to the normal subjects. So in that way, it is an indirect way of getting the perceptual knowledge effect onto a more generalized framework for identifying the health condition. Of course, this is an expanded view of the ear, where it is essentially shown there is an eardrum where the acoustic preservation come and hit on that, which will create vibration like diaphragm. From there, it goes through the mechanical bones to the inner ear. Suppose if there is a malfunctioning ear also, then the information transmission will not take place. Again, inner ear, there is a basilar membrane. The sensing cells are not working properly. That will also result in loss of the intelligibility given to the person. So all these things I can measure indirectly by giving pointed question to the subject and getting the response. Now that response, if I have such data collected from a large number of users, then I can use in the machine learning and deep learning framework for building models to do such things. Otherwise, you can see the manual labor involved in collecting data for each of the cases and do it. That is about the significance of speech for health condition. Now we'll go to the machine learning and deep learning. Maybe any questions up to this point? I'll just pause for a minute. If you have any of you have any questions. Because the afternoon session is a very sleepy and boring session. So that's where, okay, I'll continue. Just give me 1 minute break. Already about 50 minutes. I'll just take 1 minute break, 5 minutes break, say 2 to 3 minutes. Sorry. Okay, let us start. So,
Sir, there was a question in the chat box, sir.
chat box. Yeah, so that's a very good question. See, that is where when we collect speech data from different accents, of course, if you say I have data only from one accent, but when we are going for machine learning and deep learning framework, that is what I meant now in the introductory slide, that diverse scenarios means diverse accents. We are able to collect the speech data, and then when you train the model, it will normalize with reference to different accents. That is one flexibility available when you have data collected from different accents. If that is not there, absolutely there is no problem. When you are trying to train a model for a particular for modeling or identifying the particular biomarker, you are trying to emphasize that point by averaging out with reference to the accent. Of course, what will happen is, suppose you have built the model on one accent and trying to test on the other accent, maybe that may be the question from Kaushik. In such scenarios, we may have to do some adaptation. Accent adaptation we have to do. But nowadays, while during training the models itself, you have a multi-accent data for that particular biomarker, and then that issue will be taken care. Okay. Any more questions? Okay. Let us proceed. So, till that point in the introductory part, I mentioned that speech signal can indeed be used as an effective physiological signal for health informatics purpose. But that potential can be exploited only if we make use of some modeling techniques. Essentially, the frameworks of machine learning and deep learning can be used Then the speech signal collected from a diverse scenario can be subjected to modeling by using these approaches, and then use that knowledge as an additional evidence for the clinician or the doctor, along with the test reports they have, to take a call on a particular or identifying a particular ill health condition. So for that, so this getting some basics of machine learning and deep learning becomes important. Of course, this you might have studied as a course of elective courses or something. For the benefit of the community who are new, I would like to give a brief overview about that, because we use these terminologies very interchangeably. Artificial intelligence, pattern recognition, machine learning, and deep learning, we use them interchangeably. However, when these terms were originally coined in the literature of human-computer interaction, they had specific meaning. For example, when I go for artificial intelligence, the terminology came in the field of computing to emphasize that we are going to develop tools and techniques on a computer that will enable the computers to mimic intelligent tasks. For example, speech mode of communication is an intelligent task by humans. If I want to mimic a speech mode of communication on a computing machine, how do I mimic that? And that comes under this broad field of artificial intelligence. Why the word artificial is embedded? This is because computers do not have any cognitive system. The concept of intelligence is attributed to the cognitive ability of the humans. Since there is no cognitive infrastructure on a computer, that is where we only mimic that intelligent activity on a computing machine. That's why it is called as artificial intelligence. Thus, any computing on a computing in the computing field, anything you do which will try to mimic the intelligent activity of humans, that comes under the broad field of artificial intelligence, whether it is speech processing or this health informatics or image processing, video processing, natural language processing, anything which humans do in their daily life, and that we want to mimic on the computing machines. Those tools and techniques or the approaches, they're all under this broad umbrella of artificial intelligence. So this field of artificial intelligence refers to the approaches that enable computers to perform intelligent tasks. Coming to the pattern recognition, in that broad umbrella of artificial intelligence, if I come to the world of pattern recognition, the term artificial intelligence induced into the computing field to emphasize on mimicking the intelligent activity of humans, whereas pattern recognition came into the field of computers to emphasize that humans, when they interact with the external world, they use the concept of patterns. That is what we call it as pattern way of processing. And we are trying to mimic that pattern way of processing in a computing machine. And the tools and techniques for doing that came under the field of pattern recognition. Of course, you can do any of this mimicking intelligent activity by using pattern recognition tools and techniques. So in that way, some people use this artificial intelligence and pattern recognition as interchangeably. However, the original induction of these terminologies are meant for emphasizing certain aspects of human abilities. Coming to the machine learning, again, this is to emphasize the learning, mimicking the learning ability of humans. Please underline the word mimic. We have not have understood clearly how that happens on the human cognitive system, but we only have experience for that. So based on that, we are mimicking that learning. So learning ability of the humans. What we do as humans, we learn the pattern information from the given sensory data coming. For example, through my auditory perception system, the speech and audio signal that comes to my cognitive system, my brain discovers the patterns, unique patterns, which will be used for speech communication at a later point of time. And that learning ability, we don't know how exactly cognitive system does, but what people thought about was, when in the field of this machine learning, can I mimic the learning ability on a computing machine? That is where the machine learning terminology came into picture. Of course, what is meant by learning means automatically discovering the pattern information from the given set of features. Okay, that is where, for example, as a humans, when we learn any new information, we go and discover specific patterns which makes us to develop some insight about that particular concept. Okay, and without being explicitly, of course, in some cases we may say explicitly, but in most of the cases we discover on our own. Okay, and that is that learning ability, and that we are trying to mimic on those approaches comes under computing field, that is called as machine learning. Then the latest terminology introduced is what is called deep learning. When it comes to the deep learning, it will essentially help, it will go one more degree of flexibility in the compared to the conventional machine learning, where the deep learning approaches will not only discover the patterns, before that, prior to that, they will also discover the underlying feature representation from the raw data. Whereas in the conventional machine learning, we assume that the features are already extracted and given as data points for us, and the machine learning methods will automatically discover the underlying patterns, discover and model. Whereas in the deep learning, we assume that the raw data is given. From the raw data, we are trying to first discover the underlying representations, and then using this representation, discover the patterns. So that is why this is, from the raw data, first learn the representations and then use those representations for discovering the patterns. It is a much deeper way of learning compared to the machine learning methods that we were doing. Of course, people also use deep learning is also machine learning in that way, if you see, because it is also discovering the pattern. Even it is doing more. It is discovering the underlying representations also. So it is doing more. So in that way, people also treat this deep learning also a part of machine learning only. It is a specialized field of machine learning. So now that is why they now discriminate this field of machine learning as machine learning based on deep learning and machine learning based on non-deep learning. Non-deep learning based approach for machine learning and deep learning based approach for machine learning. For example, deep learning based means all deep learning models like convolution neural networks, generative adversarial network, recurrent neural network, any such models you use, that becomes deep learning approach for machine learning. Whereas any non-deep learning approach like shallow neural networks, support vector machines, Gaussian mixture models, hidden Markov models, any of those things before this deep learning came into picture, which we were using, they all come under non-deep learning approach for machine learning. Okay. Of course, once we know what these terminologies refer to, afterwards you can, if you want, you can use interchangeably, provided you have the clarity among the terminologies here. Okay. So just in a quick nutshell, artificial intelligence is for mimicking the intelligent nature of the human cognitive activity. Pattern recognition is mimicking the pattern discovery nature of the cognitive activity. Machine learning is mimicking the learning ability of the human cognitive system. Deep learning is again learning, which will learn both representation as well as pattern discovery. So that is the clarity among these four terminologies. Suppose if you see the dictionary meaning of the word intelligence, which will refer to experiencing, that is ability to learn and understand and use it for deciding future course of action. That is what is meant by intelligence, dictionary meaning of intelligence. That is what humans do through their sensory mechanism to survive in this field. survive in this environment. Now, what we are trying to do is we want to mimic this intelligence approach of humans on a machine. For example, what is that experiencing means? You discover, you learn, then use this learned information, deal with uncertainties and new situations. That is all that intelligent abilities, hallmark characteristics, and we want to mimic such abilities on a computing machine. Of course, coming to the field of artificial intelligence, we have two categories. Earlier, version 1 of the artificial intelligence was there, which we call it a symbolic manipulation of the artificial intelligence. For example, before that symbolic manipulation came, it was mostly in terms of data, compute numbers based on the value obtained. You take a decision or branch out or something. Whereas in the symbolic manipulation, need not be the decision need not be a numeric value. It can be a symbol also. Based on the symbol, you can make a decision. Whereas now, when we are talking about artificial intelligence nowadays, which is essentially a connectionist approach. When we say connectionist approach, we are using the deep learning model for doing that. So, coming to the pattern recognition, when we wanted to mimic on a computing machine this pattern way of discovery, we, in our own knowledge as scientists and engineers, that we developed a model, a block diagram approach for what a pattern recognition system should look like on a computing machine. It will have a sensor, it will have a feature extraction block, it will have a model creation block, and it will have a comparison block. These are fundamental elements for a pattern recognition system, which is essentially, for example, if I take this one, sensing mechanism will represent the auditory ears or auditory perception system when you go for speech communication. Feature selection is the representations which are put onto the auditory nerve. Model creation represents the models that are developed in the cognitive system. Comparison is during testing, how we can use those models for understanding the message that is being present in the given speech. So in that way, people brought their own block diagram approach for pattern recognition, and that block diagram was used in a generic manner for any task, pattern recognition task you use. Whether it is face recognition, whether it is fingerprint recognition, whether it is person authentication or speech recognition or handwriting recognition, the block diagram, generic block diagram. So the sensor depends on the what type of data or what type of signal you are looking into. If it is image, it should be, the sensor should be a camera. So with all that research, they were able to demonstrate that the pattern recognition approach indeed can be mimicked on a computing machine. But what the ultimate result at that point was, before this deep learning came, they were able to conceptually mimic the concept of pattern discovery. However, the performance was much inferior compared to human performance. Of course, naturally, the question comes now, why are you comparing with a human performance? Why can't you take a relative performance? No, previous version of the system gave, say, 70%. And now the next version of the system, by retraining, adding more data, it's giving 72%. Oh, my system is much better than the previous system. It is okay from a publication point of view, but what is the ultimate goal here means, I have humans. Whether your performance is equivalent to that of a human performance. Human level performance is there, yes, your technology has matured enough to be exploited commercially. And that is what has happened with the deep learning models. Before this deep learning, even though they were showing some delta X improvement from the previous version of the systems or approach, but their performance was much inferior compared to human. Coming to the machine learning, how they are embedding this automatic discovery is, they pattern discovery as a very generic process, where given X and Y, any pattern that you are trying to discover, we are calling it as a function. There is a functional relationship that exists between input and output data, and this functional information is the pattern which you have to discover. So accordingly, you can map this learning process as function discovery or function learning. So that is how, then you don't need to worry about the domain knowledge. This generalization, you can use it for any task what you want to use, both for natural data and synthetic data. That is how it gives flexibility for the automatic discovery of the pattern. That is where this machine learning field became very versatile. Coming to the deep learning, we learn both features, that is representation, as well as the pattern discovery we do. What it will do is, it will try to mimic the human way of learning. Of course, it is not that somebody has dissected the cognitive system or the brain and came up with these steps. These are all again based on the experience. When we recall our daily experience of learning or mastering over any particular concept, we agree with these steps. That is, we learn from experience. When we want to learn, we need not specify everything in the beginning. You just give some basic aspects. Then once you assume the basic aspect, just go to the next level of complexity. When you are mastery over the next level of complexity, then you go for the next higher level of complexity. At each level, you bank on the learned knowledge at the lower level of complexity. For example, all of us learned the written form of the language first by practicing writing the alphabets. Once we are masters over the alphabets, then we learned combining few letters or alphabets to make valid words. Then once we learned how to write valid words, then we started writing small sentences, phrases, and then sentences. Now we are comfortable over, anybody tells something, we can quickly write it. So you can reflect back on how you learned any particular written form of the language. That essentially reflects the process of deep learning. Now in this, that is what we are mimicking on a deep learning model on a computing machine. We don't learn everything in one go. Take the raw data, apply it to the first deep learning layer. First deep learning layer only learns few information. Then the learned few information is passed on to the next layer, and that it will use this learned knowledge to get next level of higher level complexity. So that way it goes. So you can have a large number of layers in the deep learning model until your desired pattern information is discovered. This gives me a pictorial illustration to distinguish between non-DL version ML and traditional and DL. If you go for traditional machine learning, the raw input is coming. Somebody, as a scientist or engineer, they do the feature engineering from the domain knowledge. Then they extract these features, and these features are used as data points for traditional machine learning model. The traditional machine learning model will take these data points, perform the classification task. Whereas when I go for deep learning, there is no feature engineering, no feature extraction, no traditional. All things are combined into one model. Take the raw data and feed into a deep learning model. The initial few layers will perform the feature engineering job, and those features are processed further by the later layers will perform this machine learning approach, pattern discovery. Initial layers for representation, later layers for pattern discovery, so that input raw data, output directly, you get the classification. You can see the difference between, pictorially appreciate difference between traditional machine learning and the deep learning. Of course, when we talk about deep learning, we can't do without referring to the neural networks, because by look and feel, the neural networks and deep learning models look same. So naturally people get confused, and also they ask this question saying that no, if you add slightly more number of layers, can it be called as a deep learning model? Of course, one distinction, visible distinction between deep learning model and neural network is a deep learning model definitely will have large number of layers compared to the traditional neural network model or shallow neural network model. But equally, the nomenclature of deep learning came because of mimicking the hierarchical way of learning information by model. Okay, you don't learn everything in the first hidden layer. Only few things are learned. Use that knowledge to get next level of concept learned in the representation learned in the next layer. So the deeper way of learning, hierarchical way of learning, that is also equally responsible for getting this term as deep learning model. Now, if you go for neural network, it is yet another implementation of human-computer interaction model where they wanted to mimic the structure and functioning of biological neural networks. Again, here also the caution is there, we are only mimicking. What is the structure and functioning of biological neural network? It follows parallel and distributed processing, and that is what we are trying to mimic on the neural networks. And so that was very attractive at that particular point of time when we were very passionate about one central processor which are there in the computing. This neural network came, no, you use several processors, that is small neurons as small processors, and you have a massive connection of those neurons, and that will give me redundancy, graceful degradation, nonlinear processing. It became very attractive. However, again, there also we are able to conceptually illustrate the parallel and distributed processing. However, their performance was not up to the human level performance. However, what we are borrowing from that neural network literature is that parallel and distributed processing. The second part is automatically learning from data. Of course, in the neural network case, we were using features as input, not the raw data. But the same automatically learning from data concept is the motivation for both machine learning and deep learning. Okay, so that is where the still we continue parallel and distributed processing, automatic learning from data, we do it. Whereas when I come to the deep learning model, you don't need features, you can directly take the raw data for training the data. But what prevented people at that point of time when neural networks were there adding more number of layers? People attempted it, but what they found is when you increase beyond 3 hidden layers, they were not achieving any improvement in the performance. The performance used to saturate. That means to say any type of modification you do to the neural network structure, it was not resulting any improvement in the performance. Then people resented back, excluding the input and output layer, 1 to 3 hidden layers, you can use it for building the neural network model. Because any higher layer, it was not improving the performance, means the weights which are there in the hidden layers are not being trained properly by the data or the feature that is applied. So that was the history of neural network. And in 2006, for the first time, it was demonstrated that no, it is indeed possible to try a deeper network which will have many layers. Okay, and that gave a breakthrough for the field of deep learning. Okay, that was called as greedy layer-wise training, where you train each hidden layer separately as a feature extractor and then bring that as a block and stack them together to get a deep learning network. Then use it, the stacked network with some fine-tuning using backpropagation learning as a deep learning model for any particular task. What they showed was the performance by that deep learning model was significantly better compared to earlier version like this shallow neural network or any other traditional machine learning model people were using. That caught the attention of the researchers. Of course, this point I have told. Then other researchers also in 2007, they independently verified this, and then that became a starting point for significant improvement in the performance in all sorts of pattern recognition technologies in the field of human-computer interaction. Of course, now with that, people have started proposing their own new models and new learning strategies, new way of architecture. So many things have changed from 2006 to now. But the seed point was that breakthrough work that has happened in 2006. Earlier, when neural networks were used, we were always thinking of only dense connection. Every neuron in every layer should be connected to every other neuron in the next layer. You are not supposed. There is no great theory or any mathematics behind that. People used to, but now people are ripping it apart. Earlier, when you have a shallow neural network, it is like a black box, 1 to 3 layers, you tie up together, apply input, select the output, only analyze the output. Now, with the deep learning model, we have the capability like, we can dissect each layer, you can take separately, apply the data, collect the output for that layer, try to understand or interpret what is going on. If you are not happy, you try to model that hidden layer. So in that way, so many flexibilities have come now in the deep learning model compared to that. Even learning strategies have changed, and very new deep learning models have come, like generative adversarial network, which are very new compared to the earlier cases. Of course, just to see the link between machine learning, if you see the genesis of machine learning is in pattern recognition. Machine learning is a pattern recognition where I have in machine learning, we emphasize more on automated pattern discovery. Whereas similarly, genesis of deep learning model is there in the neural network, because structure and functioning wise, it looks same, but deep learning models are much more powerful. Suppose if you take some of the terminologies like convolutional neural network, recurrent neural network, LSTM, these were all proposed earlier itself in the neural network literature, but they were unable to demonstrate their working. Okay. That's where, even though publications are there, it did not get that attention what was expected. Now, with this computing infrastructure, we have a large amount of digital data we have. Since they are data hungry models, now we are able to demonstrate their usefulness. This I have mentioned that when I take deep learning, depth is not only in terms of number of layers, but also in terms of the number of learning functions or concepts that we are learning when you have more number of layers in the deep learning model. If you see the deep learning model nowadays, there are two activities which will stand out, as I highlighted earlier. One is the representation learning, the other one is the pattern discovery. Representation learning means it essentially refers to feature extraction, automated feature extraction from the raw data by the way of nonlinear processing. Of course, earlier signal processing is the main block for representation learning or feature extraction, but that limitation because it is guided by prefixed linear processing. Whereas if you want to really appreciate the human way of processing is a nonlinear processing. That is where the deep learning models, all the neurons are nonlinear computing elements. So it will do nonlinear processing of the raw data. So with that respect to whatever the representations, feature representations that are learned by deep learning models, they're expected to be better modeling the information compared to the conventional signal processing based approach. That is where this representation learning has become very important. Similarly, pattern way of processing. So far, I did not tell what is meant by pattern. That is an important term. We have to understand the distinction between pattern and data. Data, we are very aware. In a computer, anything you want to process, you have to give it as a data. Whereas when I say humans, they only look for pattern. That means to say, we don't pay attention to the data or values associated with that pattern. We wanted to understand some distinctive information, gross information, which enables me to distinct this concept from the other concept. That is what we call it as pattern. For example, when I say the word bus, all of you will get into your cognitive system what a bus looks like. Okay, of course there can be different types of buses, different shapes of buses, but bus means you will not have any confusion of a bus with reference to, say, car or a bike, and that is the concept of pattern. Whereas on the other hand, if I take a digital data of a bus and a digital image of a bus and load into MATLAB and see, it is just a two-dimensional array, you will not be able to, looking into that data of two-dimensional array, you will not be able to say whether it is a bus or a car. Okay, that is what is meant by pattern. So if you starting from the field of pattern recognition to machine learning to deep learning, the whole effort is to develop abilities for the computing machines to do pattern way of processing. Even though computer accepts and processes data, you have to build one more layer, like your OSI model in the networking. You have to have one more layer which processes at the pattern level. Okay. Of course, now when I'm saying both representation learning and pattern discovery is happening by a single model, deep learning model, such things we call them as end-to-end system. Now this is the era of end-to-end systems where you apply raw data and get the discovered pattern at the output layer. Okay, so that is why it is called as end-to-end system. So two things which are hallmark abilities of deep learning are representation learning and the pattern way of processing. When I take an end-to-end system, it will do both representation learning as well as pattern way of processing. Briefly, if I look into the representation learning on a speech task, any doubt up to this point? I will go for this one. So I gave some introduction with reference to any clarifications with reference to the concepts of AI terminologies that I introduced. Okay, let me go to slightly more into the representation learning. So suppose if I take the speech signal, I record through the microphone, a time domain waveform looks like this. This time domain waveforms, if I process it by a signal processing method and construct a time frequency plot, it looks like this. Because since in case of speech, the information is stored as time varying functions of different frequency components, this is a more realistic representation of the speech signal from processing point of view. And this we call it as spectrogram. Now, for representation learning, when we say we are using the raw data, we are using the spectrogram. That is also a raw representation of the speech signal. There are no reduced dimension features we have here. It is still even further expanded version from time domain to time frequency domain. Intensities represent, these contours will represent specific seats. So you can see the contours here different compared to the contours here, and which in turn different compared to the dark intensity contour, which shows that these are representing different sounds. Now, in case of representation learning, we need to take this as the raw representation and further process them to extract a feature level or pattern information. For example, representation means maybe I will further stylize these bands to represent unique formant contours, the resonant frequency contour that can be treated as features. Then pattern means I will label this as which sound is that. That is the pattern discovery part. So now the question comes is, there is a history of about 5-6 decades of feature engineering using digital signal processing. Now, why are you using these deep learning models to do this feature extraction? Can't we do using only the digital signal processing? Of course, we can do in certain domains like speech or image, those things. However, if you take any other digital data, man-made, not natural, but synthetic digital data generated from digital transactions and other things, which do not have a domain knowledge, there feature engineering becomes slightly cumbersome or difficult because I don't have, because when I'm doing feature engineering using DSP, I'm completely supported by the domain knowledge of that field, but that may not be available in many fields. At that point of time, this feature engineering becomes an issue. So that is where it is good to bank on the deep learning models for discovering the representation. So that is where to expand and the scope and easy applicability of machine learning, making learning algorithms less dependent on feature engineering, which we can achieve by using deep learning, will enable us to apply this AI and deep learning to newer areas. Otherwise, this feature engineering, since requires domain knowledge, becomes it is a stumbling block for the spread of the use of technology in different areas. Of course, when I come for representation learning, you are giving raw data and models are learning representations. Oh, what is this? Is it anything unique? No, there are already earlier in the literature, we have some concepts like PCA, principal component analysis, linear discriminant analysis, if you see them, there also, if you wish, you can directly apply the raw data and get the principal component. That is how we do when we want to construct the principal component. So that can be treated as a non-deep version of the representation learning. Okay. So even we have non-linear way like kernel PCA or generalized discriminant analysis. These are also examples for representation learning. Even people tried earlier, at least in the field of speech, they took the features and trained the neural network models, shallow neural networks, and the output from the neural networks are used as representations or features for building speech recognition systems. You can see that the outputs from the neural networks, which we can directly use for classification, in place of that, they're used as features and then used in stochastic models like hidden Markov model toolkit for doing speech recognition. So the concept of representation, they did not call it as representation learning, but they felt, no, I can use neural network also as a feature extractor. Now we are using a very well thought out and well appreciated, widely appreciated terminology called representation. Similarly, there was one more attempt by using shallow neural networks for representation learning, where conventional speech recognition, we used to do short-term processing, where we consider speech of 10 to 30 millisecond duration. Whereas in the representation learning, they used to use a segment of 1 second duration. Of course, this violates the stationarity assumption. That is why they consider only a very one specific frequency component. The variability within that frequency component, we may treat it to be stationary over longer duration, and then use a neural network to extract the outputs. That people felt that this acoustic modeling output is better. That is how they use exploit neural network for representation learning. Now the same thing we are extending using the deep learning models nowadays, where we use much more powerful deep learning models like convolutional neural networks for deriving the representation. For example, the starting step can be any variant of the spectrogram. Basic version of the spectrogram is by short-term Fourier transform spectrogram, or any variant, any pre-processing you have done by other signal processing method to emphasize the spectrographic information. You can use them as raw representation for a time. Of course, you can use any of the deep learning model. Suppose I want to do representation learning using supervised deep learning like deep neural networks, recurrent neural networks. On the other hand, when I go for unsupervised thing, I can go by autoencoders, restricted Boltzmann machine, or deep loop networks, otherwise variational autoencoders, GANs, and any other unsupervised way of things we can. If you see representation learning, of course, I'm explaining feature learning, but now recently people have expanded this representation learning to include more areas, like even dimensionality reduction can be treated as representation learning. Data denoising can be treated as representation learning. Discovering the underlying cluster structure can be treated as representation learning. Disentanglement, that is from the combined dimension, how do I open up the individual dimensions? That is the disentanglement. Can represent multiple activities that we do it on in the pattern way of processing. Of course, there are different approaches for learning the representations. You can go by supervised learning or unsupervised learning, semi-supervised learning. All of this you may be aware. Transfer learning. Again, in the transfer learning, we have many variants now. One is what we call domain adaptation was the earlier thing which came. Now we have multitask learning, self-taught learning. Then we have reinforcement learning. Any of these representation learning strategies can be employed. Now, if you see an analogy for, if you see the current performance of deep learning models, their performance is almost equivalent to human level performance in some tasks. When I say like that, they have also become like experts, like human experts. So accordingly, we can call them as deep learning based expert system. We had the concept of expert system earlier, where the human expert experience in any particular domain was coded as a set of rules. So given facial images of say 100 people, if he is a forensic expert, how he recognizes under different illumination condition, different masking condition, how he is able to still say that he is the same human expert, and that is that expert knowledge that person has. If you ask him on what basis you decided or zeroed in down to this face, modified face as this person only, he or she will explain. You look at this particular portion, this is how it looks, that is how it looks. So based on that, so that is what is called human expert. And people put that as in form of set of rules and then wrote a program to mimic that. And that is called as knowledge-based computing system or expert system they used to call. Of course, they conceptually again mimicked the human expert behavior. However, their performance was not comparable to real human experts. Now, if you see these deep learning models, end-to-end deep learning models, they are behaving like human experts, that expert system. That we can treat current generation deep learning model, what is that they are doing? They are doing like a deep learning based expert system. Of course, all these things would not have been possible. We are telling, bragging too much about the deep learning models. As I mentioned in one of the earlier slides, these DNN models were there earlier itself, like CNNs, RNN, time delay neural networks, LSTM, all were there at that point of its time itself. They were unable to demonstrate at that time. How they are able to demonstrate? Maybe the timing was not good at that point of time. In late 80s or early 90s, when they proposed these deep learning models, see, at that time, computing was not that great. Even the amount of digital data was not available because digital connectivity was not like now. So naturally, so you now itself, when you want to train a CNN model on data set, we are taking days together or even weeks together to train one model depending on certain task. These days together would have become years together at that point of time, because this days together is on a GPU platform we are talking about, which has much higher power compared to conventional CPU. So naturally, it is unthinkable at that point of time. The computing infrastructure was not there. Digital data, large amount of digital data was not available. Fortunately, now the success of deep learning is to be attributed to the development of computing infrastructure as well as easy way of collecting the data. Okay, that made this current generation of deep learning based approaches as more as data driven and from domain to domain agnostic. Of course, the software complexity is more compared to the simple 10-line code we used to write earlier, and hardware requirements are also more. As I explained, hardware requirement is taken care by the GPU. Whereas software, even though we want to write more programs, these open source toolkits available by the research community can be exploited for building our systems. So that is the very conducive environment for anybody to work in the deep learning field. Now I will simply say a few results that we have achieved in the speech processing by exploiting this deep learning. Earlier, when I say past, which is using non-deep learning versions or traditional machine learning, we used to use k-means clustering or any other random forest or hierarchical clustering. Such clustering technique we used to use, or even generative model based clustering, dynamic time warping for template matching, Gaussian mixture models we use, hidden marker orders or highly successful stochastic models, shallow neural networks for use, support vector machines for use. These are all traditional machine learning models whose performance was not up to the mark like human learning. Whereas now we are talking about using deep feed-forward network, deep belief network, deep autoencoders, generative adversarial network, convolution, so on, and time delay networks, RNN, LSTM, and transformers. All these things have significantly improved the performance. For example, if I take a Anyway, in the interest of time, these things I will be sharing. You please look at. I'll go to one slide. These are all not. For example, speech recognition field. In the traditional ML model, typically the word error rate used to be around 15%. Whereas human level performance is around 3 to 4%. Now, with the deep learning model, we are able to get a performance of 3%, which is human level performance. Similarly, with speaker recognition also, earlier it was 7.5%. Now it is 4% for deep learning models. Of course, for a human level performance is slightly more than this. We are in that direction. Depends on the data set. On certain conditions, we are even able to achieve for human level performance. Similarly, for speech synthesis, generation of speech from the computing, speech, on a 5-point scale, the scores given by human subjects will be around 4.3 or so. You can see by deep learning model like WaveNet, the performance is around 4.21, which is almost equivalent to that of natural speech. So accordingly, that also has put a new threat now that we are unable to distinguish between whether it is a synthetic speech or a natural speech. Of course, that can be exploited by rogue users for some malfunctioning tasks. So the take-home message is, in case of speech technologies, using the deep learning, we are able to achieve human level performance in some of the major tasks. So as a result of that, we can indeed, suppose when I say I have a biomarker for depression, it is very, very fine level information that would be difficult to build systems if these deep learning models would not have been there. So that is where now it is ripe to use these deep learning models for healthcare tasks. For example, I'll just illustrate few healthcare tasks. If you take speech recognition, traditional speech recognition, which we are using for speech to text conversion, we can use it in the healthcare domain. Medical transcription. Now the doctor will create only spoken health records or telemedicine. Then other side, using a speech recognition system, I can build a medical transcripted version of that. Mainly because generally doctors know, all of us have experience. They don't write very legibly. They only dictate. Somebody manually listens to them and do the medical transcription. In place of that, I can now use speech recognition technology for automating that. Similarly, I can use speech synthesis for healthcare, where I can generate a natural sounding speech for conversation with the fellow users on telemedicine applications. Speaker recognition for healthcare, yes. I can use speech modality for person authentication so that when you are remotely accessing the health records, because of the privacy concern, I can first authenticate using my speech. When I authenticate, when the system comes to know that I am the same person, I am trying to access my health records, it will give out that health records for using it. Coming to some of these are the traditional speech tasks. Since now they have human level performance, you can use it in healthcare domain also. But there are tasks like which are important from a health point of view. For example, I want to detect sleepiness. Of course, we all experience that. While if due to fatigue we get sleep, when you have the fatigue, it will lead to reduction in efficiency, motivation, performance. Accordingly, it will also increase in error. Okay, so of course there are attempts for driver sleep detection system, all those things earlier, where you fix a camera and focus on the eye movements, eyeball movement, or whole face monitoring. You can do so many things are there. We can do using the speech modality also. Suppose if the person produces speech, the nature of the speech will be different. For example, if you take effect of sleep on the speech, it will have a flattened long-term information we call prosody. On the other hand, the cognitive and physical aspects will impede on the prosody things will become more, and it will have reduced intelligibility, the speech, and it may get the excitation source component may become tense, and there can be breathy qualities. Somebody sleeps, to avoid that sleep, they will take more breaths, and there will be irregular vocal cord actions. So like this, all these biomarkers get embedded into the speech signal, this concept, directly or indirectly. So that can be exploited. Of course, you can't, by signal processing method, we try to extract them, we will introduce more distortion into that. In place of that, if I use a deep learning based expert system, I will be able to do a much better job. For example, earlier they have built speech based sleepiness detection system, when they use whether based on the speech, whether you can say whether it is it will for a sleep case or a non-sleep case, binary classification. ML methods were there, which resulted in a performance of about 70%, where we were expecting 100%. If somebody attempts on deep learning based methods, we expect much higher performance. Similarly, for intoxication, people can detect whether the person has consumed alcohol or not by collecting the speech data from that person. People have attempted binary classification, whether alcohol is consumed or not. So binary classification, ML method, again, the performance is hovering around 70%. Whereas if you want to use commercially this purpose, it should be more than 95% or 99% to say that whether this person has consumed or not. Okay. DL method should be able to. Why they are only 70%, why can't I combine multiple ML methods and get it to 80%? People have tried all of them, but anywhere, the performance is hovering around that only, which shows that the ML methods, traditional ML models, as well as the traditional feature extraction by signal processing, they are brittle. They are unable to capture that fine variations which our cognitive system captures for modeling purpose. That can be now tried using the deep learning models. Even for pathological speech detection, suppose if there is a structural defect or a tumor or a cognitive effect or neurological effect, all these things will result in change in the source system and prosodic characteristics of the generated feature, which can be exploited for automatic detection classification by the deep learning models. Similarly, for autism also. If I take autisms, this it is defined by the limitations and irregularities in socialization and communication by the autistic children. So that can be, again, it will you record the speech data for a long time, you will have enough samples to understand the change in the source system and prosodic characteristics, which can be exploited. Of course, you can also there will be change in the paralinguistic characteristics like loudness, pitch, and rhythm. All this can be extracted by deep learning in a nonlinear processing, and we should be able to improve. Even, for example, for depression purpose also. So there will be change in the characteristics of the source system and prosodics generated by the speech. So, so that can be indeed be exploited by a deep learning model. So these are some deep learning based, depression material. I will just, so you can see that, suppose some of the earlier, when they do feature extraction and showed, suppose normal person, if I see the pitch variation, there is a band, whereas the depressed person, the band is different. Same way for shimmer, that other variation parameters, the zero crossing rates are different, if not variations are. So that shows that the speech indeed has a biomarker is able to capture that information for the depression information in this case. Even this variation has been shown for a female normal subject, across the subjects, this is the feature variation, whereas for the depression person, which is much higher. So that way, all these cues are available. Of course, when I say all these things, what is the efficacy of that? As I told, the performance is, they're able to demonstrate that yes, these biomarkers we can indeed capture from the speech for different healthcare tasks, However, their performance is much inferior compared to human level performance. That is where these deep learning models can indeed help us to push the boundaries to the next level. One of the things that we face to use speech processing for healthcare is less data. We may not have enough data for training the model. That is one of the bottlenecks for using the deep learning models. Of course, there are a lot of innovations are happening in terms of using different architectures, augmenting the data, and using the concept of generative adversarial network to generate more data. And also, suppose if I have a continuous way of monitoring, it will give me more data, and also in the multimodal fashion. Then any of these speech health related tasks is a very fine level cognitive task by the humans experts, well trained cognitive process. How to mimic that on a deep learning based expert system is the future course of action that we have to look into. Of course, there are many other things. For example, you build a language proficiency system that you can exploit it for many healthcare tasks. Even you can do a cognitive abilities testing task, which you can use it for some health related task. Similarly, you can use it for intent prediction and discourse. All these things can indeed be useful for healthcare related domain. So just to summarize, there is a significant progress in adding values to the computing machines, like machine learning, deep learning from the framework point of view. We have GPU infrastructure, open source toolkits available. All these things are very good support systems to handle intelligent tasks. Starting from pattern recognition, we have reached to the deep learning era. So deep learning, which has resulted in several speech technologies which provide human level performance. So which says that we can indeed exploit these attempts of deep learning, machine learning and deep learning. When I say machine learning, which is essentially I'm asking about deep learning, will definitely add significant value for health informatics area. Of course, the challenges are there in terms of limited data, all those things that we should see how to circumvent that. But we have a framework which can give good performance, significantly better performance compared to the earlier things. I think with that, I will stop here. Thank you very much for the patient listening. If you have any questions, I will be very happy to take them. Of course, there is one question here. Can we use sleep detection by wave pattern EEG models like ECG in CVDCG by using DNA? Yeah, we can do that. There is no problem. We can do that. Maybe if I go for EEG data, which is much more noisy compared to speech, then you may need a many more layers of deep learning models compared to speech. Suppose speech, if you're able to achieve by say 10 layers, this may require 100 layers and much more data, very high order of data, because it's almost like a noise. So discovering becomes a challenge there. Okay. Any more?
Participants, ask your questions, please.
Okay. If there are no more questions, thank you very much.
Is there any more questions, participants? Okay, so I hope there are no questions. So, sir, thank you, sir, for today's session. And it was an honor to learn from you. And I hope the participants have learned a lot in this domain. And thank you for being a part. And from the entire department GUIST and Gauhati University. I thank you for all your effort and pain and giving your time to us.
Okay.
Thank you, sir.
Thank you very much, Jyoti, and thank you all for participating in this session. All the best. I'm mailing the slides. You can share it with the participants. Thank you.
Sure, sir. Thank you, sir.